Trends in stability of higher oxidation states. In a higher oxidation state, how the elements of 3D series are stable. Let us have a look over that. Let us take titanium. Titanium, the atomic number is 22. So it will be argon 3D2 4s2. So this titanium will be comfortable in the form of Ti4 plus, right? Or it will form bonds with the halides. Let us say that TaX4. So tetrahalides are more possible in the case of titanium. So TaX4 is more possible in the case of titanium because here it attains a noble gas configuration of argon. It gives away these two electrons here, right? So that it attains a inert gas configuration of argon. So tetrahalides are possible in the case of titanium. The question may be why tetrahalides are possible in the case of titanium. Okay. Next, vanadium. The atomic number is 23. So we can simply say that what we can say VF5 is possible here. VF5 because electronic configuration will be argon 3D3 4s2. So if we gives away these 5 electrons out, it will reach the electronic configuration of this argon. So when vanadium is treated with, when it is give 5 electrons, it reaches the noble gas configuration. So vanadium is stable in VF5, that is vanadium pentafluoride. And in the case of chromium, atomic number is 24. So the electronic configuration will be argon. So 3D4 4s2. So it will be comfortable in the case of 6 plus. It will give 6 electrons. So it will be comfortable. It will be stable in the compound CrF6. CrF6. So this is stable here. So up to this in the lower oxidation states, the fluorides are stable. Here in the higher oxidation states, MnO3F. Here the manganese is in +7 oxidation state. +7 oxidation state. Because the oxygen is -2, so -6, the fluorine is -1. So -6 -1, that is equal to +7 here. And in the case of FeX3, so Fe is nothing but 26, that is argon 3d6 4s2. So if it gives away 3 electrons, 2 from here and 1 from here, so it reaches to argon 3d5, right? So X is comfortable or stable at FeX3, any halide form, right? And in the case of COF3, so cobalt is 27. So the electronic configuration will be argon 3d7 4s2. And here the thing is 3d6, because if you remove 3 electrons from here, 2 electrons from here and 1 electron -1 from here, so it will become 3d6. So this 3d6 is stable. Why this is stable? This is an important question. In COF3 or CO3 plus is possible. CO3 plus is possible due to higher lattice energy. Due to higher lattice energy. Higher lattice energy. Right. CO3 plus is possible. This is stable at 3d6 position due to the higher lattice energy. Vanadium, as we know, vanadium is 23. So the electronic configuration is argon 3d3, 4s2. So if you remove these 5 electrons, it will be stable and it will reach the inert gas configuration. So then V5 plus that reaches the stable gas configuration, so that vanadium pentafluoride is stable. And in the case of CrF6, chromium hexafluoride, so chromium atomic number 24, the same thing, that is argon 3d4 4s2. So if you remove these six electrons, then V6 plus will come to the noble gas configuration, so that it is more stable. In both the cases, these are all more stable. That is VF5 and CrF6. They are more stable due to the reason higher bond enthalpy. Higher bond enthalpy. Higher bond enthalpy. And in the case of VF5, only halides available in the case of vanadium is only VF5 or VX5. We can say that VX5 because other halides, if it is available, other halides, that will undergo hydrolysis, and they form oxohalides VOX3. They form oxohalides VOX3, right? In the case of V5 plus, except fluorine, no halides is available for vanadium in the plus 5 oxidation state, because all other halides undergo hydrolysis and they change into VOX3, that is oxohalides. They get converted into oxohalides. And next point, note it down. Fluorides are unstable at lower oxidation states. Most important, lower oxidation states. Fluorides are unstable at lower oxidation states. Let us consider this case. In the case of vanadium dihalide, that is vanadium, we know that vanadium is 23, so it will be Ar3d3 4s2. We know that the 3d3 is stable to what reason? CFT splitting, crystal field splitting. Right, just now I explained in 3d3 in d orbitals, there will be 5 orbitals that will get splitted into two levels, that is T2G and EG. And this T2G is, here it has 3 electrons here, so that it is stable. That is V3 plus is stable. Sorry, V2 plus is stable. It have 3 electrons in the d orbital, right? And here this VX2 cannot be fluoride. Because of the reason the fluorides are unstable at lower oxidation states. Is that clear? The fluorides are unstable at lower oxidation states. And next, copper with fluoride is not available always. We didn't see that. Not available. We didn't see CuF. Because of the same reason, the fluorides are not available in the lower oxidation state. So this may be a reasoning question or assertion reason for you. CUF is not available, not possible, and this is assertion. CUF is not possible, and this may be the reason, right? And this may be the reason, right? These are all help you in assertion reasoning part, right? And next, regarding copper, one thing we have to know that is all the other halides are possible. That is Cu2, Cl2, CuF2, no CuCl2, right? This is not CuCl2, CuF2, CuBr2. These are all possible, but CuI2 is not at all possible. This is also an important question. CuI2 is not at all possible because the Cu2 plus, it iodides, it converts, it oxidizes the iodide ion into iodine. It oxidizes iodide ion into iodine. So Cu2I2. So let us balance this equation. So here 2 and here I2. So 4I minus. So the concept is the copper, the Cu2 plus ion, it converts the iodide ion into iodine, right? It converts iodide ion into iodine. So that this Cu2 plus, because it is Cu2 plus, na? I2 means Cu2 plus. So I2 minus, this is not at all possible because the Cu2 plus will convert this iodide ion into iodine. Most important question. Iodide ion into iodine. Is it clear?